Starting thanking the organizers for inviting me. I spent one of my sabbaticals here at ITAMP, and it's a very nice possibility to coming back. I've been a couple of times since then, various workshops, but one more is very nice of coming here. So when I was told that I'm supposed to give a summary lecture, I asked what it should be, and they told me, well, it should be summary of the session in which you are the leader. I was a little bit disappointed because I would prefer to talk about my research, and I see I was naive because other people with summary talks, at least two of them, didn't understand it this way. Well, later, Hossein told me, well, you can interject a little bit of your work. So I will start from the interjection. Okay, so just obvious thing, which was said many times, the potential element surfaces, which I will talk about once developed ab initio, which I called apes, are cornerstone for any work in molecular scattering or spectra of molecules. So there are not so many methods which are universal and available for fitting those potential surfaces to ab initio data. So one of the methods was presented by Joel. It's permutational invariant polynomials. Then Joel also talked a little bit about neutral networks and Gaussian products, and then Roman talked a lot about Gaussian product today. So I will talk about three methods. Actually, I will talk about two methods. One is autoserve method from Missouri University of Science and Technology, developed by Richard Dawes. I will talk briefly about it. Then CAMCASP is developed by my former student Alston Miskita. It's very similar to what we do, so I will not discuss in detail, and I will discuss our method, which allows you to develop completely automatically potential surfaces for any molecules. In fact, very large molecules. We can do it for molecules containing like 30 atoms. I don't think any other method can do. With rigid monomers, I have to say. So let me start from discussing this autoserve. It's a very nice method, which has really quite a lot of advantages. It's a very good idea. It's called interpolating moving least square method. So what does it mean? It means that you choose two regions. Say you have some dimer. You have two regions in the dimer, fairly small regions, and for two regions you do very accurate least square fit. And then you choose another region, and so on. So each fit can be pretty simple because it involves small part of molecule. The problem is how to move them, how to connect them. So Richard has an algorithm, and this moving word, interpolating moving word, is kind of telling what it is doing. It basically works on the flight and gives you some linear combination of those various local fits as according to some algorithm. The strength of this method is very universal. You can do anything. It doesn't know if it is a van der Waals dimer or some molecule of any shape. It can be made almost arbitrarily accurate at no particular high cost. So whatever accuracy you want to get, you get it. But it doesn't have, it has incorrect asymptotics. That's one problem. And the other problem is that it's locally noisy. This interpolating moving scheme is great, but it is noisy. That's the problem. On small scale, but it is. And in spectroscopy, it sometimes matters. So our method is called AutoPS, because we call it because it's completely automatic. It's based on a method which is called symmetry adapted perturbation theory, SAPT. And I will briefly tell you what is this method. So, kind of standard way of calculating interaction between molecules is to calculate energy, total energy of the dimer, and subtract energies of monomers. Very simple, and can be done with any program. This method that we use, SAPT, calculates interaction energy directly. So you start from two isolated monomers, and then you build perturbation theory from the starting point to get properties of the dimer. Then, so no subtraction is involved, which has some advantages. Then what is this word symmetry adaptation? So symmetry adaptation means that we project the wave functions, product of wave functions of the monomers onto proper antisymmetry of the whole system. And it's really this antisymmetrization, which is physically equivalent to tunneling of electrons between the system, exchange tunneling, is the reason that potentials have repulsive barrier. Without this, they would go all the way down. Nice feature of this SAPT is that it decomposes interaction energy into fragments, components that everybody knows, like electrostatic energy, induction, dispersion, exchange terms. So what all physicists and chemists use, we actually can calculate. We can give concrete values for all those quantities at any distance. So the program is available online. We ask users to sign license, so we know how many we have, about 800 users. We have manuals, we have many examples. It's quite a big ecosystem of codes right now. So what we use physics-based fitting functions. So you can look at it in two ways. Actually, Joel thinks that model-free fits are better. We think that physics-based fits are better. It's a question of taste, of course. But what is really important, and it's not a question of taste, that we have exact asymptotics. So there's no long-range challenge. Our potentials are accurate up to infinity. And moreover, they are seamlessly connected to close-range SAPT calculation. So if you, in this sense, we use asymptotic expansion. So if you do calculations for very large distance, like say 20 angstroms, and you do SAPT calculation, asymptotic calculation, they will agree to like 3 digits. If you want better agreement, you go to 40 angstroms, they will agree to 5 digits. So this is the seamless connection. We can do rigid and flexible monomers, although flexible monomers is in development. This automated rigid monomer fitting software is already on the web for some time. Flexible monomer, work on it. This automatic procedure is as simple as running the Gaussian program. Gaussian program has this big advantage. If you tell just what molecule you want, it will give you answers. No other questions asked. So the same is in our case. You can use various control parameters, but if you don't know what they mean, system chooses some and gives reasonable fit. So only monomer geometries are needed on input. We have a, I think, nice method of guided Monte Carlo generation of grid points, which allows us to produce those potentials with less grid points than other methods. So we use less than 1,000 points for 6-dimensional potentials, which is not much. We use mostly a version of SAPT based on density functional theory, but the regular SAPT can be also used. The SAPT DFT is about as accurate as CCSD of T, but much cheaper because it scales like 5th power of system size instead of 7th powers, which is a very big difference. In fact, you can omit some small terms and then it will scale as 4th power only, which is basically like scaling of hybrid DFT. And as I already said, it's applicable to monomers with up to 30 atoms. And I will not talk about it, but our kind of big picture and long-term goal is to make this method usable in molecular simulations in design of materials and other stuff like this. So what will be the advantages of using apes instead of what is used now? So now people use either empirical potentials, so this E stands for empirical potentials, and in biomolecular applications kind of maybe not standard, but they can easily treat 1 million atoms for 1,000 nanoseconds, so 1 microsecond. But those potentials have accuracy of about 10 kcal per mole at the best. So they're not very accurate. One can use ab initio molecular dynamics based on the fly DFT calculations. This has accuracy of about 1 kcal per mole, just roughly. But of course, it's very time consuming. So you can maybe do 1,000 atoms for 1 nanosecond. And already this is an expensive calculation. If you have apes potential and do MD with this, basically you are in the same range as here because the potentials are not very much different. So MD is almost the same. Maybe like factor of 5, more time consuming, but what is factor of 5? But accuracy can be easily 0.1 kcal per mole. So we are going like by orders of magnitude to better and better accuracy. Okay, so going back to how AutoPS works. So the full dimensional potential is represented as intermonomer potential of system A, system B, and intermolecular potential. So for intermonomer, we can take potentials developed by somebody else. For example, Jonathan Tennyson potentials for water are very useful in this case. And we work on this potential. So it is written in a form which has first sum over atoms from system A and B, so sum of atom-atom potentials. We also use of atomic sites, but I won't talk about it. And then we have the term which gives you intramonomer effects on intermonomer interactions. So we have, again, functions which are functions of distances between monomer, atoms between two different monomers, times some function which is function of distances inside each monomer, where this R0 is some kind of equilibrium or any kind of reference distance. So this can be a polynomial or polynomial times exponential or pure exponential, but those functions V are in the following form, and that is our physics-based form of this function. So the first term describes repulsion. And this exponent, we know it has to be exponent multiplied by polynomial. This is known since the fundamental paper of Herring in 1960s. It has partial charge interactions, which of course is important for any larger molecules. And it has standard multiple expansion at large range. We also can use polarization model, of course, but it doesn't change much. So what is important that all those blue parameters are, so whole asymptotic is obtained purely ab initio. So we calculate long-range constants using ab initio theory, using calculating polarizabilities, multiple moments, and then constructing.
From CCSD.
Well, it depends. It depends. Since we use this mostly sub-DFT, then for consistency we use time-dependent DFT for polarizabilities, which gives very good polarizabilities, by the way. Time-dependent DFT works much better than DFT. Because it's not DFT, it's post-DFT method. So we, as I said, the only input is monomer geometry. Then you do this ab initio asymptotics, getting those Q's and C's. And then you generate grid, as I mentioned, using our method of grid generation. And then you perform so-called close range calculations for finite distances for those points from this step. We can use SAPT, we can use CCSD, we can use basically any method. Our program is interface to Orca, to MolPro, any method which is there can be used. Then we feed, and then we iterate. We don't iterate like Roman. what we do, we just have grid set divided into training set and test set, and if the results are not close on both sets, we iterate until it agrees. Okay, so I wanted to show here why we have, one reason that we need only 10 to the third point is that we don't even touch by finite range calculation a large part of space. So what I'm showing here is this red line, which is the asymptotic part of our potential, those blue things. And then this line is actually ab initio potential. So you can see that up to a very close distance to the minimum, this red line is good enough. You don't need to calculate any points. So you calculate points only here in this region. Okay, so a couple of examples how it works. So this is water dimer, and we compare here with various previous work, including previous work from our group. So here are various citations to various papers. So this is work in progress in collaboration with Edith Matthews and Attila Czaszar from Budapest. So those are potentials obtained in a very quick time period, no human intervention, completely automatically using AutoPS. Those are rigid potentials, and what I show here is root mean square deviation of theory from experiment. So there are a large number of spectral lines available. The spectral calculations were full exact quantum dynamics, so there are very little errors done there. What is interesting that this is accidental, that the RMSE of our current calculations, both for water meta and water dimer, is smallest. I think it's fortuitous, but it's the same ballpark as other calculations. What is interesting, however, that both potentials are rigid, because this is with published version of AutoPS, which deals with rigid monomer. Yet, apparently, the monomer flexibility effects are not that important for this system. So those potentials are from our group, and it each required many, many months of development and human time. This potential was done by one of my graduate students really in zero time. He just put coordinates of water and let it run for a week or so. So that's a big difference for us now that we can do it. And also notice that this is in wave numbers. So this has accuracy below 1 wave number compared to experiment on transitions which are sometimes of the order of 100 wave numbers. So it's a nice agreement. But in general, the agreement of all methods is decent. Now, 2 slides or 3 slides about second virial coefficients. I know the second virial coefficient is not something people here do usually, but it's a very good physical quantity to judge potential, because it gives you overall measure of accuracy. You have to have all regions of potentials accurate to get good virial coefficient, and very good data, experimental data, are available. So this is the H2CO molecule which was discussed here, and experimental data are those black points. So there are a couple of outliers, but generally our calculations agree with experimental data very well. And moreover, our calculations have error bars, as you can see. Error bars are obtained by estimates of accuracy of ab initio calculations, accuracy of the field, and also accuracy of path integral Monte Carlo calculations. Everything is full dimensional, fully quantum. So if you want to improve it from the point of view of physics, you have to use relativistic effects and QED. But it agrees very well, and in fact, our results are used by people in thermal physics as basically the benchmarks. And potential from Joel group, Young et al., also does very well. A little bit worse, but still really well. Those are very sensitive results. So, but to get this agreement, we had to do CCSD T parenthesis Q CBS extrapolations, and we estimates the potential has about 0.1% uncertainty. Okay, another second virial coefficient for water. So again, experimental to see the differences. Those two things are very close together if you plot the whole potential virial coefficient. So this is difference between theoretical and experimental value. So experiment is this line here, 0 line. And experiment is very accurate above 500K, basically about one wave number, so like this accurate. So you can see that this CC pole potential that we developed is very close to experiment, and MB pole potential, PIP type potential of Einstein et al. Also does very well. And again, this is full dimensional, fully quantum. This is actually a place where actually it's not only interplay of theory or with experiment, kind of confirming experimental information. Our data are right now already used by experimentalists. So basically, experiment is very accurate above 500K, but it's not accurate below. And really, experimental error bars, I didn't want to make it too busy, are of the order of our deviations from this experimental correlation. And in fact, most likely, our results are more accurate than experiment. And also, in long range, theory is used by those experimental correlations. And then very hard, third virial coefficient of water. It's really very hard because it depends almost exclusively on three-body potential. Two-body potential gives very small contribution. Experiment here is not accurate. Again, I simplify this picture in our paper, which will be published sometime later. You will see all those error bars. Those are averages of experimental results. Agreement is not so good as for second virial coefficient, but it's still decent. And again, as I said, we cannot say that experiment should be replaced by theory, but at least we give some hints which experimental data are probably more accurate, which are less accurate. Okay, so now summary. So I did try to summarize what we discussed at this meeting in this session that I was leading the discussion. So one thing discussed was who is the driver? And I think that the general agreement is that both are the drivers. So scientific development drives development of software and vice versa. It was noted that virtually all development, a large part of development in AMO is now based on computational work in theory. Then Jeppe emphasized differences between electronic structure theory, like quantum chemistry, but also solid state programs are very similar, and this simulation field. So compared to this, AMO software is very fractured. There are few recognized software packages, like say those that Jonathan just presented, but most of packages are mostly known to the authors and a couple of people who are very close to this particular field. So should we keep it this way in AMO? I think everybody agreed that it's not the way to go, that we would like to have high quality, free codes available, and it will lead to a faster progress in our field. So what are the ways to improve this current situation? We are pumping some money into it. So I say that this is my reading, and you may disagree with this, but I think that it would be good to get support for proposals which include code optimization. Philip have shown us that it's very, very difficult to get such support. I was able once to get, I had good support for like 5 years from DoD, but it was 15 years ago. Then one thing which would help is to create some cyber infrastructure institute for AMO, similar to the one in Virginia Tech, which Lincoln has shown on one of his slides, and we discussed it a little bit on the way. What I think would be really very important, I mentioned it in the last discussion, is to create central catalog of AMO software, but at much larger level of detail than what is in Wikipedia. Actually, there's nothing in Wikipedia for AMO research, but what is in Wikipedia, say, for quantum chemistry research. And then this is connected closely to what Jonathan was talking. So in UK, they have for years support for code development. And I benefit from it. We use a software called DL-Poly, which is a molecular dynamics package, which is a very good package. What is important is that it is all the time developed. They have new versions which are better and better. They have now one version which works really very well on massively parallel computers, which certainly required a lot of effort and funds to develop. They have help. They do help you. I mean, my students greatly benefit. I sometimes say, don't bother them, ask me first. But they still prefer to write email and they get answers. So this works really very well, and we should think about supporting groups which maintain such codes. Well, we first, actually, in AMO, we have to create such codes, but once they are created, they should be supported in such a way. There's one issue which was not particularly discussed, but I wanted to mention it because it's kind of something which bothers me. Should federal agencies support commercial software? So they do right now, but it also depends what software. Like, say, I like what Jonathan was saying. So R matrix code are available for free. If you want additional, bells and whistles, you pay. So that's okay. But I think that in many cases, those programs are kind of obstructing science because they are never available in source code. So if something happens and they cannot help you, you are completely on your own. And I had several cases like this. And also, in case of my group, we need several codes. Each of them, some are less expensive, some are more expensive, but if you buy all of them, it's a significant use of grant money, and moreover, it's not one-time purchase. In many cases, you have to pay like yearly license. So I am for developing free software packages. They can be easily disseminated by putting them on group websites, central depository. I'm not against it, but it's not really something which we need badly. If such packages are supported, it's very important that there's a clear requirement that they are well documented, because nobody will use packages which are not well documented. Some user help should be also funded, and for example, if the Software Institute was formed, this would be an ideal way of doing this. And also it would be good if this kind of fractured situation in atomic software was changed, and one kind of package which would have many options would be built out of those many codes. And I wanted to briefly say about my last effort of getting software funding, because I think this is something which, at least in this case, NSF didn't do well. So this is the Scientific Software Innovation Institute, and University of Delaware submitted a proposal with participation of several other people from various institutions. So this is the announcement of this. I will let you to read it. And there's like maybe 2 times as much, basically in the same vein. If you know what it means, what kind of proposal you should prepare, maybe you can explain to me. We actually called and emailed several NSF contact listed on this, not AMO, because this proposal was really aimed at material design. So we didn't get any helpful information. So we submitted this proposal for multi-scale simulation in science engineering All those pictures are from actual work of people who participated in the proposal. And the main thing was that we will build a single software package which will be interfaced in such a way that somebody wants to work on this kind of batteries, this person can actually start from quantum mechanics and get some information. And we said that it's a long way, that it's a very ambitious project, but the problem was that really we didn't get any scientific response. The only response was responsive low. So we apparently misunderstood what is here. Okay, so thank you.